Welcome to Notebook. In today's video lesson, my friends, we are going to study motion and time. Motion and time are two very familiar concepts to us. By the end of this session, you will be able to differentiate between slow and fast motion, define speed, measure speed, and identify the unit of speed. If you look around, my friends, there are some objects that are immobile and some that are mobile. Can you name some immobile objects? Well, we see all kinds of immobile objects around us, like TV, radio, statues, and others that cannot on their own. And then there are mobile objects such as trains, cars, trucks, rickshaws, and buses. Mobile objects are those that can move, and we see plenty of them around us. What about objects moving very fast, my friends? We know that trains and aeroplanes move very fast. Rockets fly faster. So, by our naked eyes, we can distinguish some transports that are fast and some that are slow. How do we distinguish such fast and slow movement? The key distinguishing factor is speed. Suppose Harry takes 5 minutes to run across a circular track field, but he wants to run faster. On the second day, he is able to run the field in 4 minutes, saving himself 1 minute on the track. So evidently, Harry was running the track at a higher speed and would calculate speed by dividing the total distance travelled by Harry by the total time taken by him to cover it. Distance is in the numerator and time is in the denominator. In this case, the track was of 500 meters and Harry increased speed, hence he took 5 minutes initially, which later changed to 4 minutes to cover the same distance. So initial speed was 500 divided by 5 into 60 is equal to 1.67 meters per second. Time should be converted to seconds during calculation with meters, and therefore we are multiplying number of minutes by 60 to convert it to seconds. If distance is given in kilometers, time is expressed in hours. Now again we can calculate the final speed of Harry by the equation of speed, which is equal to 500 by 60 into 4 is equal to 2.083 meter per second. So Harry was covering 0.41 meter extra every second to cover 500 meters in 4 minutes. The unit of speed is therefore given by meters per second or kilometers per hour. This brings us to the conclusion that distance remaining the same, that is, if the value of the numerator in the speed formula remains the same, the time value falls. The speed of an object increases. Just like Harry, speed of objects can increase or decrease with change in distance values in a given time. This gives rise to uniform and non-uniform motion. If your bus travels to school in 20 minutes every day, we see that the bus reaches school in uniform motion. It takes the same time to cover the same distance every single day. What if this is not always true? What if you are late for school and the bus driver decides to travel faster? Say for example, the first 10 kilometers was travelled in 1 hour. The speed is equal to 10 by 1 is equal to 10 kilometers per hour. And now in the next 30 minutes or half an hour, the bus covers 8 kilometers. Then speed is equal to 8 by 1 by 2 is equal to 16 kilometers per hour. We see the bus is covering more distance in lesser time and therefore speed increases to 16 kilometers per hour. When speed of objects increase over time, we call it non-uniform motion. Here we see a comparison board between uniform and non-uniform motion. For uniform motion, it's always equal distances at equal intervals of time, and for non-uniform motion, it is unequal distances at equal intervals of time or time unchanged. Remember, uneven distances at equal intervals. We see here that in uniform motion, every 5 minutes a distance of 10 km is covered. But for non-uniform motion, 25 km is covered in the first 10 minutes and then 5 km in the next 10 minutes. So speed actually falls. If you want to graphically depict distance and time over graphs, you will see that in uniform distance time graphs, the same block of distance is covered during the same block of time. And why not? Distance from 0 to 10 meters is the same as distance between 10 meters to 20 meters and so on and so forth. Similarly, time spent from 0 to 1 and 1 to 2 seconds is again the same. Every block on this graph shows that same distance is covered in same time. This is uniform motion and it therefore follows a straight line. In comparison, think of how a graph of non-uniform motion would look. It will be the same x and y axis. However, different distances would be covered in the same intervals of time. The graph would no longer be a straight line. It would in fact become curved. In this case, the speed of a body increases over time and hence it is an increasing non-uniform motion. Now, will you be able to look at distance and time graphs and say whether they depict uniform or non-uniform motion? Let us show you a few examples. A free falling object is an example of non-uniform motion. A ball gains momentum as it falls. Imagine a ball is at rest with no change in distance. The first graph shows what happens when a body is at rest as distance does not increase with passage of time. This is a flat line. Others we have discussed under uniform and non-uniform increasing and decreasing motion as curves upward increasing or falling respectively. So now with a fairly good idea of how speed is measured, you must know about a few instruments that measure time. There are sand clocks that effectively measure time. Apart from regular clocks that we use, these instruments have been used in the past by humans to measure time. Sundials do the same job of measuring time. We have sundials in different parts of the world. These measure time according to the location of the sun. One final time measuring device, and the most wonderful one, is the pendulum. Pendulums have a point of suspension, a massive bob that moves from one extreme corner, say A, to another, C, and then back to its original position at A. This is called the pendulum's trajectory. B is the equilibrium position. The time taken to cover one whole trajectory is referred to as the time period and is called one oscillation of the bob. Galileo Galilei, a famous scientist in the 16th century, worked with several pendulums and found that those with a given length of wire always take the same time to complete one oscillation. This observation led to the development of pendulum watches. Later on, winding clocks and wrist watches were refinements of pendulum clocks. With this, we come to the end of the chapter on motion and time. Hope you have enjoyed the session and stay with us for the rest of the chapters to understand key concepts. Thank you for watching and goodbye.